Hi, welcome to the third session on inner product spaces. Today we are going to look at a finite dimensional inner product space, okay, with an inner product. Okay, if you fix the basis, okay, can we recover? Okay, if I know the value of the inner product on the basic elements, do I can I get the inner product? Okay, I'll explain on the way. The main result we want to look at is using this information how to construct new inner products in R2. The way we do, okay, actually generalizes to all vector spaces over R, of course, or also over C, but it will take little more theory to prove it rigorous there. So we will stick to R2, but that will give you an idea, okay, how to construct new inner products. Okay, that will be a good thing. So let us get started. Okay, so suppose let V be a finite dimensional inner product spaces. Okay, this I will denote by IPS. Okay, right. And let Vi 1 less than or equal to I less than or equal to n be a basis. Okay, recall that the inner product, okay, is a map from B cross B to R, which is bilinear. That means, okay, the map X going to inner product X Y naught fixed, Y naught in V. Okay, this is a linear. This is a map, linear map from B to R. Similarly, the map Y going to X naught Y, X naught in V fixed is linear from V to R, right? That's what it means to say it's bilinear. Now recall from the early theory, if this is any two vector spaces, okay, let V and W be vector spaces, not necessarily inner product. Okay, suppose F is a linear map from V to W. Assume it is finite dimensional, right? Let Vi be a basis of V. Then what do I know? If I know f of Vi for 1 less than or equal to I less than or equal to n, then I know f of V for any V in capital V. Okay, let's quickly go through the proof. This you must have seen in a slightly different way, but this is the most important thing. If you had gone through my linear maps videos, you would have said, okay, to understand linear maps, okay, it's important. You should not worry about the expression for linear maps, but you should look at its action on a basis. Okay, that I had explained. I hope you will go through it. Okay, suppose V, since it's a Vi is a basis, I can write it as 1 to n. Okay, linear. Therefore, f of V is using linearity xi f of Vi. Since I know f of Vi and I know how to write V as a summation of xi Vi, then I know what is f of V. That's what this means. Okay, quickly pause in case you have not seen it earlier. Pause, review, and then proceed. Okay, right. Now, since it's this map, now let us look at V inner product spaces. Finite dimensional inner product space, Vi is a basis, right? Now this inner product is bilinear, but then what does it need? It requires two arguments, right? So what will be the correct thing I want to say? If I know f of Vi, then I know f. Now how do I say about something about the inner product's action on some basis? If known something, how will I say that? Remember, inner product needs two things. Therefore, if I know Vi Vj, for all I and j, okay, suppose we know inner product vi vj, okay, then we know, then we can compute inner product v with the w for any v and w in capital B. This is what we want to prove. Okay, please understand what we want. Okay, there f of vi, here what do we want? Inner product of vi with vj for all I and j I know. Do I know from that can I compute inner product of v with w? Is that clear? Huh? Make sure that you understand the question. As I said, questions are very important to understand. Do not jump into answers. Okay, then answers you can only memorize, you cannot see how it answers, what questions it answers anyway, right? So we will proceed as usual. But this is a fact which we should learn, but let us see. Suppose I write v as summation xi vi, okay, I equal to 1 to n. Hereafter I may skip, okay. Teachers always write such things. Sometimes, I am very impatient. Okay, this is the expression linear v is written as a linear combination of basic elements w, right? Therefore, what should be vw? How do I compute? This is what I find many students have problem. But if you have gone through the first two lectures, I told you the secret. How will I do? I will think of this as summation xi vi and summation yj vj, right? Then think of it as an ordinary multiplication. It will be xi vj vi yi vj, but then that multiplication inner product xi vi, sorry, let me do it. Okay, this will be xi vi summation yj vj. I will think of this as summation this product this, right? If you have summation of xi in ai into bj, what will be this? This will be a bj, right? Take an arbitrary summon here, multiply. Okay, so this is the arbitrary summon. What is arbitrary summon? That is xi vi and multiply with yj vj. But remember, in this case multiplication means what? Inner product for me, and then the summation is over I and j. But then this is an inner product, therefore the scalars come out. Therefore this is I and j, xi comes out, similarly yj also comes out, then vi vj. Okay, since these are already known and I know what are xi yj, because v is summation xi vi, w is summation yj vj. Remember, I and j are dummy indexed. I can as well write summation xi vi, summation yi va also, but then in a hurry you may look at it like this: xi vi and yi vi. Then you may think inner product is xi yi, inner product vi va. Do you see that? That's something like a famous thing, a plus b whole squared is a squared plus b squared. Kaisa 2ab extra aya. Okay, that's the question. Okay, so it's better to write this carefully. Have you understood? So let us pause. So xi vi, notice that this could be anything to anything, not necessarily the same thing n, but anyway let us stick to that. Yj vj j equal to 1 to n is summation I and j xi xj, sorry, xi yj vi vj. This is 1 to n. Okay, so please make sure you understand this formula. This is what you should learn thoroughly. Okay, of course there is a PRP here. Make sure you understand this, feel comfortable. Once you have learned this, okay, you should not worry about. It's almost like ordinary multiplication, except remember, when you are multiplying two vectors, you should think of this as an inner product. Simple, that's it. That's the only trick. Okay, good. Now come back. So how I proved it? So if I denote by aij for 1 less than equal to I less than equal to j less than equal to n, aij equal to inner product vi with vj. Okay, these are known now. Then If V is summation xi vi and W is summation yj vj, then inner product Vw is summation aij xi xj I and j equal to 1 to n. Right, where aij is inner product vi with vj. Okay, again just make sure you understand this. So what does it say? Just because I'm using bilinearity, if I know these objects, then I know inner product of v with w for any two arbitrary vectors v and w. Right? Okay. Next, what we want to do is something special about this matters. What is aij? Aij is inner product vi vj. But what do I know? Remember, we are in a real inner product space. What is vi inner product vi vj? It is same as inner product vj with vi. But then what is this? This is aj. Therefore, what is the conclusion? So for all I and j, okay, aij equal to aj. If j equal to I, there is nothing. Yeah. In particular, if I form the matrix A, whose ijth entry is aj, then this is a symmetric matrix. Do all of you understand this? So, given an inner product on V and a basis Vi, then I have found a symmetric matrix. How did I find the symmetric matrix? Its ijth entry is nothing other than inner product of Vi with Vj. Right? So, do you understand this? Therefore, the inner product, okay, is completely determined if we know the matrix A. Why? Because if you give me inner product Vw, and if I know V is xivi using the basis, and this is yj wj, then this fellow is nothing other than aij into xi yj. You follow that? Okay, this is the first step. So given any inner product on a vector space, finite dimensional vector space over R, and if you have fixed a basis, okay, the inner product is completely determined by a symmetric matrix. How is the symmetric matrix decided? That is given. The ijth entry is inner product of the ith basic vector with the jth basic vector. Okay, are you comfortable? Okay. Now I can go ahead with the R abstract vector space as over R, but let me stick to, because I want this to be accessible to BSc students, so I want to stick to Rn to make ideas clear, right? And we take this basis, the standard basis, that is our ei 1 less than or equal to I less than or equal to n. So our VIs are standard base ei. Now I will think of this as a column vectors. Therefore my E1 will be 1 0 0 0 etc., and En will be 0 0 0 1, right? And therefore any vector x is x of E1, sorry, x1 of E1 plus xn of En, that is column vector x1 x2 xn. Okay, again, if you have seen all my earlier lectures on linear algebra, you should be very confident about these things. Okay, right. Instead of the usually algebra teachers will write as a row, I am writing as a column. Okay, good. Right, now suppose this, I already have a dot product on Rn, right? What is that? X dot y is equal to summation xi yi I equal to 1 to n, right? Now I just want you to think slightly differently. Again, those who have seen my linear algebra, linear maps, etc., where I always look at Rn as a column, okay, set of column space of column vectors, you will know this. This, let us look at, if X is in Rn, I can think of as a vector, a matrix of type n cross 1. Therefore, X transpose will be a matrix of type 1 cross n, right? Therefore, let us look at this matrix X transpose. This is 1 cross n, and the matrix Y, this is n cross 1. Therefore, I can do multiplication of these two matrices, right? The product of these matrices, and the product of these two matrices is a 1 cross 1 matrix. That means this is only one, and there is a real number here, right? So that real, what is that? Let us just look at it. This is x1, x2, xn, and y1 to yn, and this matrix is going to be x1 y1 plus x2 y2, x2 y2 plus xn yn. That, let us write it as summation xi yi I equal to 1 to n. Okay. Notice that there is only one entry here. Okay, so it's a usual practice, the standard convention. A 1 cross 1 matrix is identified with its entry as a real number. That is, if I have a 1 cross 1 matrix, this is identified with alpha, where alpha is null. Over any field also it is correct, but let's not worry about it. Please understand one case very thoroughly, the other case are very easy. Is this clear to you? So what I have found is, if x and y are an Rn, x dot y I can write it as x transpose times y. Okay, where this is a 1 cross 1 matrix, but I don't think of it as a matrix. I think of it as only the entry, which is a real number. Okay, please understand this. This is for all x and y and Rn. Okay, right. Now comes the next step. Okay, let this be an inner product, a possibly new inner product on Rn. So from what we know, we already know, okay, if I put Aij equal to inner product of Aej for all Inj, right, then if x is summation xi ei and y is summation yj ej, then what do I know? I know that inner product xy is summation aij xi with yj imj running from 1 to n. We all know this, right? Now comes a very important observation. This is a very beautiful thing. This is the real crux of the matter, where it says, okay, if I know one inner product on a vector space, any other inner product can be recovered in its, how to write it, it will be very clear. Okay, please understand, these are the things which are very beautiful. Okay, this you can see, I can write it slightly different way. Okay, I want to claim this is nothing other than ax dot y, where this is the usual dot product. Remember, A is my Aij, which is an n cross n matrix, and x is an n cross 1 matrix, therefore Ax is n cross 1. Okay, this is also n cross 1. These are vectors in Rn, right? But Ax dot y I know is nothing other than Ax transpose dot, okay, Ax transpose y. This is a matrix of type 1 cross n. This is a matrix of type n cross 1. Please pay attention, do not get psyched. Okay, these are all easy. But this is nothing other than X transpose A transpose. You know that for any two matrices, A B transpose is B transpose A transpose, I'm sure all of you had already learned these things. Therefore, this is A transpose into Y. But remember, A is symmetric. Therefore, A transpose is A. Therefore, this is nothing other than X transpose AY. Just relish this. Okay, you have a new inner product. Okay, this new inner product. Okay, for any two vectors X and Y, these are all in Rn now. Okay, this is given by X transpose A and Y, which is Ax transpose, sorry, Ax dot Y. This is a matrix of type what? 1 cross n. This is a matrix of n cross n. This is n cross 1. Therefore, I get a number. Right? So, the beauty is this new inner product is got in terms of A and the standard dot product. So, what have we learned? So in summary, the inner product is expressed in terms of the matrix A and the standard dot product. Okay, this is very beautiful. Just spend some time, understand what you have shown now. Okay, right. So let us recall what I have done now. So I have shown that on Rn you give me any inner product, alright, then I can express that in terms of a symmetric matrix and the standard dot product. How did I get the symmetric matrix? That is the inner product of Ei with Ej with respect to the new inner product. That's it. That is my Aij, right? It's very beautiful. Right? Therefore, any new inner product comes out of dot product and some symmetric matrix. Isn't it beautiful? So what is the next question you would like to ask? If I start with an n cross n symmetric matrix, okay, can I define the new inner product xy equal to ax dot y? That is same as X transpose AY. Can I do that? Will this define an inner product on Rn? Is the question clear? As I said, unlike many teachers, I insist my students should understand the question. They should spend more time on the questions, more time on the definitions than learning proofs of theorems or solutions of exercises. Okay, come back. So the obvious question to ask, of course, with real entries, okay, if you let inner product xy, where x and y are of course in Rn, to be ax dot y, which is X transpose AY, does this or is this an inner product on Rn? Is the question clear? Very good. Okay, now let's look at, in general the answer is no. Okay, we will look at this. This is in general. What are the things which can go wrong? First, notice that, first of all, note that the map xy going to inner product xy, which is X transpose AY, which is ax dot y, this is bilinear. See, you put something is inner product What we want the first thing is positive definiteness, that is inner product v must be greater than or equal to 0 and equal to 0 if only if v is 0. After that we want the inner product should be bilinear. That's what we do, led by x plus x dash inner product y equal to x dash inner product y plus x plus inner product y, etc., etc., and similarly scalar, right? Okay, so essentially only two conditions. First condition is positive definite, second condition is bilinearity. But the map you are defined here is a bilinear map automatically. That's very easy to say because it's because of matrix multiplication. Because what will be x plus x dash? That will be x plus x dash, right? X plus x dash and transpose ay. But remember, matrix multiplication is again distributive. Therefore, it is x transpose ay plus x dash transpose ay. Therefore, this is inner product x dash y or xy and inner product x dash y. And similarly, scalar multiple. Therefore, and again with respect to y, you can do similar thing because it will be x transpose a y1 plus y2, right? Or y plus y dash, that will be ay. Are you following what I am saying? X y plus y dash, this will be x transpose a y plus y dash. But again remember, matrix multiplication a plus b, this is distributive, that is ab plus ac. Therefore this will be x transpose ay plus x transpose a y dash, but this is xy xy dash. Okay, and similarly scalar multiple. Therefore this is clear. Okay, make sure you understand. Pause, review, proceed. So what remains to be shown, therefore, okay, so the most crucial property is now positive definiteness. Right? Okay. So now I don't want to do general Rn. Now we will restrict ourselves to R2. Okay. Right. So let us write down a symmetric matrix A. Let A be a symmetric matrix. In 2 by 2 symmetric matrix, because of conic sections, there is a reason why conic sections appear here, but that will come if you read my linear algebra book, you will know, and perhaps I will come to that little later. See, when you write a quadratic equation in two variables, conic sections are given by a quadratic polynomial in two variables, right? How will you write it? Ax squared, then you write as 2hxy plus by squared. Do you remember that? So for that reason, I will write this as a, h, and h and b, where a, b, h are real. Okay, otherwise you natural way would be to say b, 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 c. You understand? But I just want to write it as h because of, okay, there is a beautiful thing, there is a relation between what we are doing here and conic sections also, but that has to wait for a long time. But is that clear now? This is a symmetric matrix, right? Now let's look at the simplest symmetric matrix, 1, 1 and 1. Okay, let us do that. So suppose this is a symmetric matrix AHHB. This is my symmetric matrix, and therefore what is the inner product of two vectors? Let us say V and W. Now I will stick to the standard coordinate system. Okay, x1 y1 and x2 y2, these are vectors in R2, right? So what is the new inner product now? VW. Okay, instead of doing that, we'll just look at this is x1 remember this is, what is this? This is V, that is column vector, that is x1, so sorry, x1 y1, because this is a column vector x1 y1 and its transpose is what we should do. Then A is AHHB and x2 y2. Do you understand that? Let me write. Somebody complained about my handwriting, because I'm more worried about, I'm thinking, okay, I'm not trying to recall something. This is x1 x2 y2. Go back to the definition. What is this? This is x transpose A x. This is the formula. You understand that? And we also said it makes sense because this will be 1 cross n cross n, and n cross 1. That is why we got. Okay, right. So I hope I wrote it correctly. So let us do that. This is x1 y1 and this is ax2 plus hy2 and hx2 plus by2. So when I multiply this out, first row by column, this is going to be x1 times ax2 plus hy2 plus y1 times hx2 plus by2, right? So let us look at this. This is a x1 x2 plus h x1 y2, and this is y1 x2, therefore it is x2 y1 plus b y1 y2. Do you follow that? Therefore the new inner product xy is ax1 x2 plus h into x1 y2 plus x2 y1 plus b y1 y2. Okay, pause, review, proceed. Yeah, I just did it for this case, right? Now let me take the matrix A to be 1 1 1 1, or so let us see. No, see, we want the first thing. What is the first condition for positive definiteness? Inner product VV must be greater than or equal to 0, right? I want to know. See, let us look at a diagonal matrix A. 1 and minus 1, 0 here. Is it symmetric? Yes, of course, right? Therefore, what is the inner product of this using the above formula? Remember, h is 0, therefore it's going to be, and my inner product BV is what I'm looking at, right? And suppose B is xy, right? Therefore it is x1 equal to x2. Therefore this is ax squared and this is b y squared. Do you understand that? Because h is 0. Therefore this is ax squared plus by squared. Make sure you understand this. Yeah? And now let us look at. Therefore if I take, for example, something, my x equal to 0, y equal to 1, that is e2. My vector v is e2. 0, 1. What do I get? I'll get 0, and b is minus 1 and y squared is 1, therefore I get minus 1. Do you follow that? Right? Therefore, okay, not all symmetric matrices will do. Give rise to an inner product on R2 via VW going to V transpose AY. Right? Because the first condition is violated. Okay, maybe the first condition is okay. The next thing, something. Oh, I wanted to say it's 0, right? Yeah, that's right. It's an A. Now let's look at next matrix A 1 1 1 1, and let's look at the vector E1 plus E2, right? Then what happens? Let's look at again. We'll go to the formula. This is 1 1, therefore A, the inner product, this is my V, inner product VV is ax squared plus 2hxy plus by squared. Yes, okay. So let me look at E1 minus E2 then. So this is 1 minus 1. Therefore what is A? A, H, B, they're all 1. X squared, X is 1, therefore this is 1. And plus 2, what is H? H is 1. And what is Y? That is 1. But Y is minus 1. And plus B is 1, Y squared is 1. Therefore this is 1 minus 2 plus 1, that is 0. And remember, E1 minus E2 is not a 0 vector. Right, so I have inner product VV is 0 though, but V is not equal to 0. Therefore, positive definition is already violated. Yeah, very good. Okay, and let's do one more thing. This is all fun. Okay, and suppose notice that. Do you notice that something very interesting? In the first case, suppose A H H B, right? Therefore, with respect to that, inner product BV is ax squared plus 2hxy plus by squared, right? Now suppose I take E1, B equal to E1, then I get only A, right? But since B is non-zero, inner product BV must be positive, therefore it implies A is positive. PRP, okay, positive view thing. In fact, I should have put PRP a little earlier, but I forgot. Okay, so what did we see? In general, if I take a symmetric matrix, positive definite is not assured. Okay, inner product, so I will call it inner product. Okay, inner product of VV could be negative, that we saw, and inner product of VV could be 0 without B being 0. Okay, for a non-zero vector, inner product VV could be 0. So not all matrices can define inner product. So now we already get one sufficient condition. Therefore, if I have a symmetric matrix, okay, the first condition I want is A is 0. Similarly, B is also 0, because if I take B equal to E2, what do I get? If I take B equal to E2, this is 0, this is 0, but then this will be B, right? Therefore, B is positive. So necessary, these are the necessary conditions. Okay. Next, the determinant of AHHB, okay, cannot be. It should be non-zero. Let's look at the second condition which I wrote, 1 1 1 1 1. This one determinant is 0. Okay, and if you remember your linear algebra well, you see, this is how I try. My students find my lectures difficult because I always try to relate to what you all learn instead of simply sticking to only this fellow. Notice that if I have this 1 1 1, this defines a linear map from R2 to R2. How does it define? The xy going to 1 1 1 1 xy, which is x plus y, right? Now this can have a kernel, because I want this to be 0, right? This is a linear map. Okay, this is a linear map, and it has a kernel because x plus y must be 0. That means y equal to minus x. So in particular, the entire line, this one, sorry, wrong, this line, y equal to minus x, okay, this lies in the kernel. In particular, the point 1 minus 1 is there. Now let's look at the inner product. Please pay attention. Okay, at base level you may find it difficult, but just go through once second time, you will see how much you are confident about your linear algebra and inner product space. Now, what is my definition of inner product? Suppose B is in the kernel now. Okay, kernel of A. I will simply call this linear map also A. Not necessarily this. Assume that, okay, let A be equal to A H B, okay, and determinant of A is 0. Okay, let B be non-zero vector in the kernel, where A depends a linear map from R2 to R2. Right? Then what do happens? What is the inner product of B with B? Remember, that is by definition B transpose AB. But AB is already 0. This is a 0 vector. Right? 0 vector of what kind? N cross 1. And this is a B transpose. This is 1 cross N. Therefore, this is 0. So, yeah. So necessary conditions, okay, are A is positive, B is positive, and AB minus H squared is not 0. Right? But again, if you look at the case 1 minus 1, okay, what is AB minus H squared for this? That is minus 1. And we know this is not positive definite. Right? So what do you think you should expect? Make a guess. I can prove, but since the time is running out, I don't want to spend much time. What is that you should expect? Yeah, you should expect AB minus H squared must be positive. Okay. So let A be a matrix A H H B, so that A is positive and AB minus H squared is positive. Notice that B is positive will be automatic. Okay. Why? Because you understand this? Right. Now you look at that. AB minus H squared. Right. This is positive. That means AB is greater than H squared. Right. And H squared is greater than or equal to 0. That means AB is positive. But I already know A is positive. Therefore, B must be positive. Do you understand that? AB minus H squared is positive. Alright. But therefore, AB is greater than H squared. H squared I do not know. H may be 0. Therefore, it's H squared greater than or equal to 0. But then, AB is strictly greater than H squared. That means AB is positive. But A is positive. Therefore, B is positive. Therefore, okay, necessary condition I can say A is positive and AB minus H squared is positive. Okay. Now I am going to prove, okay, assume A H B is such that A is positive, AB minus H squared is positive. Then the map XY going to X transpose AY is an inner product on R2. Okay, pause, review, proceed. Okay, as usual, it's important to understand what we are saying. The proof will follow easily. Right? So, assume A satisfies the conditions. Okay, and let V equal to XY, then inner product VV according to us is AX squared plus 2HXY plus BY squared. Right? We already know the map. Okay, BW going to inner product BW is bilinear. Okay, therefore I need only to check positive definiteness. So I have to show this is greater than or equal to 0 and something. Right? Let us prove that. So this is right. So what do I have to show? For every X and Y in for every xy in R2, I have to say this is greater than or equal to 0 and equal to 0 if and only if x is 0 and y is 0. Right? Okay. How do you do that? This is where you have to recall your high school trick. Many of you may remember ax squared plus bx plus c. What are the roots of this equation? All of you know, minus b plus or minus square root b squared minus 4ac by 2a. Right? And you kept on using the formula throughout your course, and I usually find very rarely less than 10% of the students remember how they got this formula. Do you remember? Yeah, I'm not sure. Anyway, okay, it is what is known as completing the square. That's a trick. That is ax squared plus bx plus c. What you do is you take, if a is 0, there is nothing, it's not a quadratic polynomial, right? Therefore a is non-zero. Take a out, therefore x squared by b by ax, okay, plus c. Right? So what do I want is, I want to write this as a square. This is a square if I take x plus b by 2a. Do you understand this? But when I take x plus b by 2a whole squared, that's going to be x squared plus b squared by, I hope I'm writing it correctly, yeah, 4a squared, yeah, plus 2 times this, that is b, 2 times b by 2a into x, therefore 2 times bx. Therefore this is the term extra b squared by 4a squared, but remember there is an a out. Therefore what is the extra term? That is b squared minus 4a plus c. Yeah, right? This I can write as minus b squared minus 4ac by 4a. I hope I did correctly. A squared plus bx, right? This is b by 2a, that's very correct, right? Yeah, I multiply, I get it. Therefore b squared minus 4a squared, that's also correct. Okay, let us see if there is something wrong. I will find out. Therefore x plus b by 2a whole squared is, okay, minus 1 by a into b squared minus 4ac by 4a. Okay, therefore this is going to be 4a squared common and minus of b squared minus 4ac. Okay, therefore my x has to be minus b by 2a plus square root of this fellow, square root of b squared minus 4ac by 2a. Yeah, got it. Is this clear? Very good. Right. So that's what we want to do. So what we have, the inner product VV for v equal to xy is ax squared plus 2hxy plus by squared. Therefore I am going to complete the square. That is going to be a, I take out. Remember a is positive. Therefore x squared plus 2h by a into xy plus by squared. Right? But that is equal to what? A. This I want to complete the square, that is x plus, this is 2, therefore h by a y. Do you remember? X squared plus h squared by a squared into y squared plus twice h by a into xy. I got it. So what is the extra term? There is an a out. Remember, a into the extra term is h squared by a squared y squared plus by squared. Right? Therefore, this is a into x plus h by a y whole squared minus this a cancelled. Therefore, this is this. Therefore, y squared is there. Therefore, h squared minus ab by a into y squared. Yeah, but that is same as a into x plus h by a y whole squared plus ab minus h squared by a into y squared. I hope I did not make any goofing. Just make sure. Yeah, right. Now let's look at a is positive. By assumption, ab minus h squared is positive. 1 by a is positive. Therefore, these terms are non-negative. Both the terms are non-negative. Therefore, the sum is non-negative. Is that clear? Make sure you understand this. Right. Next, when it is 0, if it is 0, each term must be 0. Right? Equal to 0. Suppose inner product v is 0. That means first term is 0. That is equal to second term. That is also 0. But let's look at concentrate on the second term. That is ab minus h squared by a into y squared is 0. But this is positive. Therefore this implies y is 0. Right? Now plug it in. Therefore in xy, this is x comma 0. Therefore what is the first term? First term is a, go back, x plus h by a y squared, but y is 0, therefore it's a x squared is 0. Therefore first term becomes ax squared, and suppose this is 0, since a is positive, this means x is 0. So I have proved x is equal to y equal to 0, that is b is 0 vector. Right? And as I said, positive definiteness is a crucial thing. We proved it. By linearity is very general. Right? Okay. Just as an leaving exercise, I did the special case. Remember, suppose A is an n cross n symmetric matrix and write column vectors x1, x2, xn, then the inner product xy, we already got it, but let us do that. X transpose a11, a1n, an1, ann into y1, y2, yn. Okay, this is equal to x1, x2, xn, and this is summation a1j, yj, and so on. anj, this is 1, not I. Okay, anj, yj, and multiply out, then you will get summation aij, yj. Remember that this is equal to x1 into a1j xj plus x2 into summation a2j, sorry, yj, and so on. Therefore this I can write as summation xi summation aij yj, j running from 1 to n, I running from 1 to n. This is equal to summation aij xi yj summation I over ij and over to n. Okay, this I could have done in the when I did 2 by 2 case. Okay, I just wanted to do the general, that's why I did that. Okay, right. So for some of the BSc students, it may be especially demanding. My suggestion would be, as usual, team up with a friend of yours, go through, watch it twice. Believe me, if you go for MSc, you will really thank me. Even after MSc, these things are never taught properly. Okay, right. I hope all of you enjoyed. Now we have created a new thing. Now take a very concrete numbers, A, H, H, B. Okay, with what are the conditions? A must be positive, determinant must be positive, and write down the inner product. And now complete the squares and prove that it is a definite, it's a positive definite thing. Because you have learned how to do that by completing the square. To make sure that you never forget this trick, do that. Are you following what I mean? For example, I can take 5, 2, 2, 1. That's a symmetric matrix. Or similarly, think of anything. You could have taken 2, 1, 1, 1 also. Right? Write down the inner product defined by this matrix and check it is positive definite, right? By completing this way, right? I hope all of you enjoyed. We will meet again.